To train a physical AI agent, the system must accomplish two highly coupled tasks. It has to understand the current state of the world, and it has to simulate plausible future outcomes. Historically, researchers have treated these requirements as separate engineering problems, resulting in a fragmented, sequential pipeline of discrete models. This diagram maps out that standard pipeline. It typically starts with a vision language model to reason about the environment, which then passes its outputs to a completely separate vision language action model to generate a physical policy. To evaluate the consequences of those generated actions, the system relies on yet another isolated network, a forward dynamic simulator. Cosmos 3 architecture collapses this multi-step handoff. It brings all of these isolated functions into a single framework. By encoding language, video, audio, and physical action into one unified token space, the system processes every modality through a shared mixture of transformers backbone. Agents no longer pass data between isolated architectures. Reasoning, simulation, and execution are computed natively within the exact same network. To achieve this integration, the model first has to translate completely different data types into a shared representation space. For visual understanding, it uses a standard vision transformer. For generating video and audio, it relies on variational autoencoders to compress the signals into discrete tokens. But the architecture adds a distinct input. It treats physical action as a first-class modality, processing it on the same level as text or images. These action representations are built from three components: ego poses for the main observation frame, effector poses for the agent's tools, and grasp states for object manipulation. Instead of getting bogged down in low-level PID controller parameters, the system abstracts the motion into pure state differences and structural geometries. This mathematical projection shows how an SE3 kinematic delta, representing a change in position and rotation over time, passes through a domain-specific projection matrix to become a single latent action token. Because this projection is optimized jointly with the main backbone, these action tokens operate in the exact same mathematical language as the text prompts. Mapping diverse robotic controls into a unified geometric token space enables the model to output executable physical commands directly from the simulator. Once all modalities are tokenized, they must be arranged carefully to prevent interference between the logic of reasoning and the mechanics of generating. This horizontal block illustrates the sequence packing protocol. Every input is divided into two distinct subsequences, an autoregressive prefix section in blue, followed by a diffusion sequence section in orange. The autoregressive sequence holds the language text and the VIT-encoded visual tokens. This section is dedicated entirely to reasoning and understanding. The diffusion sequence contains the noisy video, audio, and action tokens, waiting to be iteratively denoised into clean outputs. To process this packed sequence, Cosmos 3 relies on its mixture of transformers backbone. Inside a single transformer decoder layer, the architecture splits into two parallel pathways, a reasoner tower and a generator tower. The routing rules are strict. The reasoning tokens from the autoregressive sequence are routed exclusively into the reasoner tower parameters. Meanwhile, the generating tokens from the diffusion sequence are routed exclusively into the generator tower. This physical separation of parameters ensures the model retains the precise text generation logic, while simultaneously learning high-fidelity physical generation without the tasks degrading each other. If the two towers use independent parameters, the generating tokens still need a way to know what the reasoning tokens are actually thinking. The challenge lies in their conflicting logic. Reasoning tasks require a causal sequence that only looks backward, while generation tasks require full bidirectional context to maintain spatial and temporal consistency. This attention matrix grid maps out the solution, a dual-stream joint attention mechanism. For the autoregressive stream, a strict causal mask is applied. Reasoning tokens can only attend to preceding reasoning tokens, completely blocking them from seeing any of the orange generation tokens ahead. The rules for the diffusion stream are entirely different. The generation tokens are granted full bidirectional attention, allowing them to scan the entire reasoning sequence and their own generating sequence to gather necessary context. By enforcing this one-way mirror, the reasoning tokens are never updated based on the generating tokens, preserving the causal integrity of the reasoning logic. The structure solves the routing, but it creates a secondary challenge for aligning time across drastically different data rates. Standard positional embeddings simply count sequence indexes. That method breaks down when trying to mix 25 Hz audio with variable frame rate video and discrete action tokens. Instead of indexing by sequence order, this 3D coordinate space tracks absolute temporal alignment. It locks each audio, video, and action token onto specific markers along a shared physical timeline. By combining asymmetrical attention masking with absolute temporal indexing, logic and physical simulation inform each other without sequence collisions. Because all modalities share this exact token space, shifting the robot's physical task does not require loading a different model. This sequence shows how the system alters its operational mode simply by defining which tokens act as clean conditions and which act as noisy targets. Here we see video tokens connected by bridging action tokens. In forward dynamics mode, the action tokens are clean and fixed. The future video tokens become noisy targets, forcing the model to calculate the visual outcome of those specific commands. In inverse dynamics mode, the objective flips. The video tokens are clean, and the connecting action tokens turn noisy. Now the system must infer the precise physical movements required to cause that observed visual change. And in policy mode, the objective for a world action agent, both the future video tokens and the action tokens turn noisy. The system denoises both simultaneously, generating the required physical intervention and its expected consequence in parallel. This unified representation means that the architecture scales across entirely different training environments and tasks without structural rewrites. Perception, simulation, and physical execution are no longer treated as distinct engineering disciplines. In this framework, they operate as a single continuous computation of how the physical world works.